Welcome to our very first ASEG webinar, and thank you so much for joining. My name is Kate Robertson, and I'm the President-elect for the Australian Society for Exploration Geophysicists. I hope everyone's doing well in these current difficult circumstances. Here on the ASEG Executive, we've been putting our thinking caps on. We're very eager to continue to deliver exciting and informative content to you all, to our members. And we're very sad that we can't meet face to face, but look forward to that in the future. So we've developed this series of webinars, and this is our very first one. And fortunately now, at least members around the world can all attend. If you do have any suggestions for upcoming webinar topics, then don't hesitate to send them to us, and you can find all our contact details on the ASEG website. So just before we get started today, I'd like to take this opportunity to express our gratitude to the sponsors of the ASEG. Firstly, I'd like to thank our corporate and corporate plus sponsors. So these sponsors provide enormous benefit to our society. They help make it possible to hold events and provide other content to our members, such as our bi-monthly exploration, geophysics and preview publications. And it also involves a significant donation to the ASEG Research Foundation, which helps to support honours, masters and PhD projects for geophysics students. So thank you kindly to our Corporate Plus sponsors, Velsize and HiSize, and thank you to our corporate sponsors, Archimedes Financial Planning, GDD Instrumentation Inc., Santos, SAE Exploration, and Southern Geoscience Consultants. We're also grateful to our branch sponsors that help to enable our regular technical events held by each of our 7 ASEG branches. Thank you to these companies. Your support is greatly appreciated. Thank you very much. Please do not hesitate to contact us if you'd like to support the ASEG through a corporate plus or sponsorship. See our website for more details. So just before we move into the talk, just a couple of quick housekeeping items. So firstly, your cameras and microphones are currently switched off, or if they are not, can you please make sure that this is the case? And you can see on this slide where you'd find the mute and the turn off your video button. So this will just help to avoid distraction from the talk. If you're still seeing any videos on your screen, if you press the minus or minimize button where the faces or the black boxes with names are, then that should get rid of that. During or after the talk, you can ask questions. So we will be having a Q&A session at the end, but you can type your questions in the chat box at any point during the talk, and we'll go through those at the end, and I'll ask them to Chloe. This talk will also be recorded, so Chloe has kindly agreed to that, and so we'll make it available on our YouTube channel afterward. And we do have, so we're constantly looking for new webinars at the moment, and we've got a few in the works, and these are the ones that we have more or less finalised the details for. So our next one is by Daniel Blatter from Lamont Doherty Earth Observatory, Columbia University, which will actually kind of be in a way a bit of a flow on to Chloe's talk today. And his title is Constraining the Resistivity of Pore Fluids in the Crust with Bayesian Joint Inversion of MT and Surface Towed CSEM Data. And then we have Pete Betts, who will be talking on the 26th of May, on the topic of crustal architecture of mineral systems using potential fields. And our very own president, Dr. David Arnetz, who will be talking on 10 years in the wild, the P223 experiment. And we'll keep you up to date on our website and through emails as we add more to the mix. So now we are on to the technical part of today, tonight, this morning, or whatever time it is, wherever you are in the world. So I have great pleasure to introduce our speaker, Chloe Gustafson, who is currently presenting from Montana, United States. Chloe studied at the Colorado School of Mines, where she obtained a bachelor's degree in geophysical engineering, then continued on to graduate school at the Scripps Institution of Oceanography, where she received her master's in earth science. Chloe is now a doctoral candidate nearing completion at the Lamont Doherty Earth Observatory, where she uses marine and terrestrial electromagnetic geophysical methods to image submarine and subglacial groundwater systems. And Chloe also does remote fieldwork in Antarctica, as well as offshore work on research vehicles. So I'll now switch the screen sharing over and welcome Chloe to present her work, Characterizing Extensive Hydrogeologic Systems Beneath Ice Sheets and Oceans Using Electromagnetic Methods. Thanks very much, Chloe. You should be able to start your screen share now, hopefully.
Great. Yeah, thank you, Kate, and thank you to ASEG for having me give this talk. It's really exciting to have people from all over the world tuning in. And just Kate, for you, I noticed there were some people still in the waiting room as you were giving your introduction, so that might be something you would want to keep an eye on. Okay, so to get started, as Kate mentioned, today I will be talking about my current research on characterizing extensive hydrogeologic systems beneath ice sheets and oceans, and I do this using electromagnetic methods. To start, I would like to acknowledge my collaborators in the projects that I'll tell you about today. There's my advisor, Carrie Key, who's at Lamont, Rob Evans at Woods Hole, Matt Siegfried at Colorado School of Mines, and Helen Fricker at the Scripps Institution of Oceanography. So my research is really motivated by one overarching question, and that is, what can subglacial and submarine groundwater systems tell us about the past, present, and future? And in order to answer this sort of broad question, we need to look at quantifying the actual amount of groundwater in these systems, and also look at how this groundwater plays a role in nutrient exchange mechanisms. And then we can also use groundwater, modern observations of groundwater, to tell us about past hydrologic conditions. More specific to ice sheets, groundwater can affect how ice flows, and that's going to play an important role in why we care about groundwater in these regions. And in the offshore environment, looking to the future, offshore groundwater may become an important water resource as traditional on-source resources are becoming more and more depleted. Now, the primary tool that I use to answer this question is electromagnetic geophysics. So that's what most of my talk will focus on today. But as with any method, it becomes a lot more powerful when we combine this with complementary geophysical data, geochemical data, and also modeling. So my talk today will be divided into two parts. So part one will be subglacial hydrogeology, and part two will be submarine hydrogeology. So to begin, I'll start with Antarctica and its hydrology and how hydrology plays a role in ice sheet processes. I'll talk about how we use electromagnetic methods to image groundwater systems. And then I'll show an example of a survey that we recently completed in West Antarctica aimed at imaging groundwater systems. So I'll start with Antarctica as a whole. And here on the left, we have ice mass loss for the whole continent on the y-axis, and the x-axis we have time. And on the right, we have these ice mass loss changes plotted spatially, where warmer colors represent region of ice mass loss and cooler colors represent regions of ice mass gain. And as we watch this animation finish, we can clearly see that Antarctica is losing ice. I don't think this is a surprise to anyone. And one of the primary mechanisms, or one of the mechanisms that Antarctica can lose ice, is simply ice flowing off of the continent and then out to its exterior and eventually into the oceans. So here I'm just plotting ice flow over Antarctica, where faster velocities are represented by these yellow colors. And we can see that the fastest regions in yellow here are ice shelves. And ice shelves are actually the floating portions of the Antarctic ice sheet. So they don't directly contribute to sea level rise because they're already in the water. But ice in ice shelves is holding back grounded ice, and grounded ice can make more of a difference in sea level rise. And the division between grounded ice and floating ice is called the grounding line. So grounded ice primarily makes its way out across the grounding line to ice shelves and eventually the ocean via these ice streams, which are these fast-flowing dendritic features that are extending back into the continental interior. And interestingly, many ice streams are underlain by active subglacial lakes. So at the base of the ice sheet, we have liquid water present. And as you can imagine, liquid water is going to affect how ice is flowing in these regions. So when we say active subglacial lakes, we're really referring to the fact that these lakes change in volume. So here we're going to see an animation of two interconnected lakes. One of this lake on the left is going to drain and you'll see the ice surface drop. And on the right, this lake will rise and the ice surface will also rise. And these ice surface changes are actually how these lakes were initially identified. So people like my collaborator, Helen Fricker, saw these changes on the surface of the ice in these isolated patches and inferred that there must be water at the base of the ice that was causing these changes. And these changes were first observed using a satellite called IceSat, and those height change anomalies are plotted with this color scale where red represents regions of greater change. So going back to our general schematic, we have these active subglacial lakes that are at the base of the ice sheet, and our ice sheet is flowing out across the grounding line where it then becomes an ice shelf. So we know a lot about these subglacial water systems from satellites like IceSat and IceSat-2 now. As I mentioned before, this water in subglacial lakes can be important for modulating how ice flows, and this has been shown by people like my collaborator Matt Siegfried and others. And these lakes can also host microbial life. So in these deep, dark, cold environments, we actually do have life, and this can be a good analog to what extreme life might look like in other extreme environments such as Europa. And you'll also notice in this figure that our lake has this pathway connecting it to the ocean. So not only do we have lake water controlling ice sheet flow, we have water actually flowing in this system as well. And these drainage pathways can transport both water and nutrients into the ice shelf cavity and in the Southern Ocean. And this transport of water and nutrients can be important for carbon cycling in the Southern Ocean, which is the largest carbon sink. Another way this transport of water can be important in the oceanic environment is that it may be affecting these complex ocean circulation patterns beneath the ice shelf, which also act to contribute to ice mass loss in some cases. So we have these satellites and they're very good at detecting water volume changes, but they don't give us the total water volume in this system, and they don't tell us about exactly where water is sourced and where it is stored. And for this last point, I'm really thinking about potential groundwater systems. So there is a modeling study that suggests that 45% of the hydrologic budget of ice streams could actually be coming from deeper groundwater systems. But right now we don't have any observational constraints on this prediction. And so in order to investigate these potentially deep hydrologic systems, we need to use geophysics, specifically ground-based electromagnetic methods. So electromagnetic methods are really sensitive to electrical resistivity, which is an Earth property that varies over several orders of magnitude for different Earth materials. So here I just have a sampling of various materials we find on Earth, and on top I've plotted conductivity on a log scale, which is just the reciprocal of resistivity, also on a log scale on the bottom x-axis. And in the case of looking at groundwater beneath ice sheets, we're interested in water here. And water itself spans about 3 orders of magnitude, and this variation is a function of ion concentration. So as you introduce more dissolved solids or salts into the system, you get more electrically conductive responses. So when we're looking beneath an ice sheet, we're really looking to image, for my purposes, water and sediments. So we should be able to get a good idea of if there's water present in the sediments and how salty that water might be. And we also have our very resistive ice. So having this large contrast is a good thing from a sensitivity standpoint. But in order to get at electrical resistivity without drilling a bunch of holes, we do need to introduce some physics. So we learned in our introductory physics classes that a time-varying magnetic field will induce a secondary electric field, and and a current. And the electric field and current are related through the conductivity. This current then will generate another magnetic field. And so we have this coupled system. And for the purposes of hydrogeologic investigations, we're really interested in conductivity. And we know our current J because we either actively create it ourselves or we're using passive electromagnetic fields, which we can determine. And then mu naught is just a constant. So if we can measure electric and magnetic fields, we can use this coupled or these coupled equations to eventually get at conductivity or resistivity, which is our property of interest. Electromagnetics have been used in Antarctica previously. Recently, an airborne electromagnetic survey was used in the dry valleys of Antarctica to map a subglacial system there. And in this case, they used a helicopter to generate a source field using this antenna, and then secondary currents were generated in the subsurface to create this resistivity image. And people have also used magnetotellurics, or MT, to investigate deep geology and in the crust, and then even down to mantle depths. And MT is a passive method where our sources are naturally induced, and one of those sources is actually lightning strikes resonating throughout the ionosphere. And one thing I would like to point out about these two figures is the scales of depth here. So here we're looking at very deep, tens of hundreds of kilometers, and here we're not even getting to a kilometer depth. So for today's talk, my research is focusing on using this method, magnetotellurics, to image the upper few kilometers, to image what I called the deep hydrogeology of Antarctic ice streams. And in order to establish magnetotellurics as a good way for looking for deep hydrogeology, we went to a hydrologically interesting place called the Whillans Ice Plain. So the Whillans Ice Plain marks the convergence of 2 ice streams, the Whillans Ice Stream and the Mercer Ice Stream. This whole region is underlain by active subglacial lakes, which are connected via these water flow paths, which eventually make their way out across the grounding line, here shown in black, and into the ocean beneath the ice shelf. So we focused our magnetotelluric survey on Whillans Subglacial Lake right here, and we were testing whether or not this lake was underlain by some deeper a groundwater system. So first I'd like to look at some recent activity of Whillans Subglacial Lake. So here these black dots represent the averaged height changes over the entire lake, and those height changes are plotted on the y-axis, and on the x-axis we have time. So the activity of the lake is pretty quiet from a height change standpoint up until about 2013, and then the lake goes through 2 filling and draining cycles before entering another quiet period. The other activity that has occurred at Whillans is geophysical activity. So in 2011, seismic and radar data was collected here. And then a couple years later, they came in and directly accessed the lake via hot water drilling. And then 5 years and 2 fill drain cycles later, we came in and completed our Magnetotelluric survey. So from a comparison standpoint of these 3 surveys, I like this plot. I think it's good. It shows that all these surveys occurred during sort of quiet periods for the lake, but I do think it is important to still keep in mind that in each of these instances, we are just taking snapshots of an evolving system. So this is what our Magnetotelluric survey over Lake Whillans looked like. Our MT stations are plotted in yellow and orange triangles. We were able to collect 27 stations, and they were spaced either 2 or 3 kilometers apart. The orange triangles also represent where we collected controlled source EM data, but I will not be discussing those results today. The seismic data that was previously collected here is shown in pink, and where the seismic data interpreted a water column to be present is noted in this darker blue color. So you can see there's kind of a disagreement between the satellite-derived lake outline and the water column derived from seismic imaging. We also have the green star where the lake was directly accessed, and there's been a GPS station out there for a while. I think Matt just took it out this last season, but this was measuring the lateral and vertical height changes of the ice above the lake. And I'll point out that the ice thickness here is about 800 meters. So this is a schematic of what magnetotelluric imaging looks like over an ice sheet. So here we have a simplified picture of our system sitting on top of ice, which is very electrically resistive, and then a lake and sediments, which are more electrically conductive, and then bedrock, which is more resistive. So we have our source field penetrating down through the ice and into the subglacial geology, and this source field then creates our secondary fields, which we measure with our electrodes and magnetometers buried in the snow. And this is what that actually looks like in the field. So we have our data logger here at our central hub, and then out from here, we plug in and we bury electrodes and magnetometers and then plug everything in here. And here I just have a time lapse of what it looks like to set up one of these instruments. We had a team of 4, and once we got into a good workflow, it took us about 30 minutes to set up a station. I think you could get away with a team of 3 and not lose very much time. So I think in future surveys, it could be good to have 2 teams of 3 to effectively double the number of instruments that you're deploying without actually losing very much time. The limiting factor would just be weather and your actual number of instruments. So when we collect this data, there are still a few more steps we have to go through. So we start out with our electric and magnetic fields. Then we need to do time series analysis to generate response functions. And then we take our response functions and we do geophysical inversion to get a resistivity model of the subsurface. And the last step is then using empirical relationships to interpret this resistivity in terms of something we're actually interested in, such as the salinity of water. So I will show you just part of some of our apparent resistivity response functions over subglacial Lake Whillans. Then we'll look at the inversion, and then I'll tell you guys how I'm starting to interpret this inversion model. So here again, we have our survey over Lake Whillans, and I've highlighted 5 stations that go across the lake, and I've plotted one mode of their apparent resistivity response functions over here, and those are color coded. So this blue station corresponds to these blue dots. And here we have apparent resistivity on the y-axis and period on the x-axis. And generally, our shorter period data is sensitive to shallower structures, and longer period data is sensitive to deeper structures. And just from looking at these response functions, we can already see that we are sensing variations over the lake, and especially in this blue site off the lake, we do get a different response function. Now, if I invert this data in a 2D sense, this is the result that I get. So here we're looking at the upper 5 kilometers beneath the ice surface on the y-axis, and we're spanning about 15 kilometers on the x-axis. And the colors here are log 10 resistivity, so the black and dark blue colors are very conductive, and the yellow and white colors are more resistive. And the 2 features that are very robust in all of the different inversion models that I've run are this very conductive feature here, and then this more resistive feature, which sort of spans the bottom part of this image. And me and my colleagues' working interpretation of these features is that we have a salty aquifer, and right now we're thinking this has to be the salinity of seawater, or even saltier perhaps, but that's going to depend on different porosity variations and temperature with depth as well. But even looking at all those different options, we do think this pore water is actually quite salty. And then this resistive feature is some low porosity basement rock. And I do have inversions for some of my other lines of data. So here we have a nice fence plot, and these are just stitched 2D inversions. And what we see here is that this really conductive dark feature extends below all of the lake. So it seems like a pretty pervasive feature, and the depths that we see in our crossing lines do match up really well. And a next step for this data would be to do 3D inversion, which we are planning on doing. But to me, this really begs the question, how much salty groundwater is there beneath other subglacial lakes and just within the whole Whillans Ice Plain as well. So I think this is a really interesting result, and it's showing us that we do indeed have deeper groundwater systems in Antarctica. So just to wrap up this section of the talk, my main takeaways really are that hydrology plays an important role in various ice sheet processes, as we went over with the schematic. We have identified groundwater beneath the Whillans ice stream, and we're seeing that this groundwater is really salty. So this is where we are identifying salty groundwater. And that helicopter survey that I briefly mentioned earlier was over here, and they also saw really salty groundwater. So I think it is likely that there's a lot more salty groundwater out there that we just haven't found yet. So next I will switch gears to submarine hydrogeology. I'll kind of go through the same workflow. I'll talk about emplacement mechanisms for offshore groundwater and the scientific and societal importance of offshore groundwater. Then I'll briefly talk about how we use electromagnetics again to image groundwater. And then I'll talk about a survey that our research group completed offshore the US Atlantic margin, where we were successful in imaging some offshore groundwater systems. So I like to start with just sort of a generic cartoon describing what submarine groundwater is, because it's not a system that we usually think about. So here I have a very simplified continental shelf environment where I have bedrock, and on top of that we have continental shelf sediments, which are mostly covered by ocean water. Now we know that continental shelf sediments are really a mix of sandy and clay layers, and I've lumped them all together for this illustration, but I would like to pull out one layer for the purpose of talking about groundwater. So here I've pulled out a confining unit, which is a very low permeability unit that makes it's hard for fluids to transmit past this layer. So one way that we could get groundwater into this system is simply modern meteoric recharge. So rain water and river water in the modern day could be filling up sediments in the onshore environment. And if these sediments are continuous and extend into the offshore environment, we have offshore groundwater. Another way that water could get into the system is during a glacial period. So when the sea level drops and the continental shelf now becomes exposed and it is a terrestrial environment. So again, we can get meteoric recharge that charges up the sediments via rainwater and river water. And if we're at high enough latitudes where ice sheets can form, water can also be introduced into these systems via melt at the base of the ice sheet and in front of the ice sheet. So time moves on, the ocean rises back up, some of this water is going to get mixed back in with the ocean, and then some of the water is actually held underground via this confining unit. So this is the type of groundwater that I'll be talking about when I talk about submarine groundwater, and it can either be emplaced in modern or paleo times. So submarine groundwater is a global phenomena. This map here shows locations where low salinity submarine groundwater has been observed or inferred, and you'll quickly see that this has been observed on every continent. And it's been estimated that there is 500,000 cubic kilometers of low salinity offshore groundwater. And to put that in more real terms, that's like 22 times the volume of water in the Great Lakes. But this estimate is actually somewhat crude. It's based on these 7 locations, which I've starred, and I'll just pull out one of these locations in New Jersey to demonstrate how this calculation works. So here we have the continental shelf in New Jersey, where the x-axis is our distance from shore, going out to about 150 kilometers, and the y-axis is down to about 800 meters below sea level. So first step is to get pore water salinity from borehole measurements. And then once you have these salinity measurements, you can start interpolating between them. And then you draw lines to make your model. So this first orange line that I've highlighted represents a low salinity contour. It's basically freshwater. And then the next line gets a little more saltier and a little more saltier as we go out. And then we pick a threshold, let's say 1/3 the salinity of seawater, and we draw a box approximately around where we've reached that threshold. Then you can calculate the 2D water volume. And this is what has been done for all 7 of these sites. So the 2-dimensional water volume was calculated, then averaged, and then multiplied by the total length of passive margins in the world. So that's how we get this 500,000 cubic kilometers estimate. So this is a really great starting point and a like totally logical thing to do, but we really would like to more accurately map these offshore groundwater reserves. And there are several reasons we would want to do that. So from a paleohydrologic perspective, if we can accurately map where offshore groundwater exists, then we can build paleo models that incorporate stratigraphy changes, sea level changes, and ice sheet dynamics, and figure out how these three things are interacting to emplace groundwater where we observe it today. Offshore groundwater can also give us information about past ocean salinity changes. So when during glacial periods, a lot of ocean water is taken up by glaciers, but some of it also stays sequestered in the seafloor. So if we can have a better idea of where that groundwater is and how much there is, that can give us a better handle on why we observe the past ocean salinity changes that we currently see. This groundwater can be important for the subsea floor microbiology. It can also be important for nutrient exchanges. So this water can bring nutrients from the continental environment out into the continental shelf and then potentially into the ocean as well, where it can affect nutrient productivity. And this last point is something I mentioned sort of in the beginning, and that is these offshore groundwater resources or these reserves could represent a potential freshwater resource. And this last point is really what gets a lot of people's attention. Now I put in this last headline because, well, I thought it was maybe a little over the top when I first saw it and like looking into things maybe a little too much, but it does bring up a good point, and that is we are, as an Earth, in a global water crisis. And if we continue in a business as usual scenario, in the next 20 years, these regions shown in red are going to be regions of high water stress. So if we can accurately map and understand offshore groundwater resources, there are clearly millions of stakeholders involved, and people could really stand to benefit from potentially being able to extract these resources in a sustainable way. So our current methods for estimating groundwater volumes are this first one, which we already went over, interpolating pore water salinity measurements. And we also do use paleohydrologic modeling to predict offshore groundwater volumes. So in this case, we're looking at offshore groundwater from Massachusetts. And here, this is the same modeling study in all 4 of these panels. And in this study, the author has just changed either the glacial forcings of the model or the permeability of the model. And I should point out that salinity is our color bar. So 0 blue is freshwater and 35 in red is the salinity of seawater. And we're looking at about 145 kilometers of continental shelf. So this is useful, but we can see from just looking at these 4 panels that these models are sensitive to different forcings and tunings of the parameters. So as you can imagine, what I'm going to talk about is another way to map these offshore groundwater reserves, and that is electromagnetic methods. And again, just looking back to our electrical resistivity chart, we can see that this is a great tool for mapping offshore groundwater because we are sensitive to water and its salinity content. So the logistical setup is a bit different than what we saw in Antarctica. Here we use surface-towed controlled source electromagnetics, where we have an antenna followed by 4 receivers. And this antenna generates electromagnetic fields, and then our secondary fields are generated in the subsurface based on hydrogeologic variations, and we pick up these fields with our 4 receivers. And this is what this looks like in a 1D case. So here we have air, ocean, sediments, an aquifer, and then more sediments. And the colors here represent electric field amplitudes. So our transmitter is here, and we can see that the electric fields that we're generating travel through these layers in different ways, especially our aquifer. We can see that the electric fields have higher amplitudes for longer, and this phase, this wave really travels a lot faster. So from a sensitivity standpoint, this is a good thing. We can see that our aquifer clearly gives a different signal than the surrounding sediments or ocean. We also use magnetotelluric methods to image offshore groundwater. And this is what we did in Antarctica, but instead of burying our receivers in the snow, we set them down on the seafloor. And this is just a sped up version of deploying one of these receivers on the seafloor. And for this particular cruise, we left these instruments out for 3 to 5 days and then picked them up. So we collected both surface towed electromagnetic data and magnetotelluric data offshore New Jersey and Martha's Vineyard in an attempt to map offshore groundwater. So I'll start with our New Jersey survey. Again, this is somewhere where we already know that there is offshore groundwater. And here in New Jersey, we have these well logs that I showed earlier, and here they're noted as these dots. So yellow dots represent where we've seen low salinity groundwater, and the magenta dots show where no low salinity groundwater was observed. I'll also point out this dotted white line, which is the extent of the Laurentide ice sheet during the last glacial maxima. So you can tell that Martha's Vineyard was probably influenced by the presence of that ice sheet. Again, we go through a similar data processing scheme. We have our raw time series, which we convert to a response function and then get a resistivity model. And I will point out one difference here is that we did do a joint geophysical inversion where we jointly inverted our controlled source data and our magnetotelluric data. And this response function is actual data from our survey offshore New Jersey. And this is electric field amplitudes from our 4 receivers. And this is, sorry, the scale seems to have gone away, but this is a function of position. So it spans the continental shelf of New Jersey. And then the black lines are our actual model fits to the data. So we can see that we do get a really nice fit when we invert our data. This time, I actually am going to start with our empirical relationship before I show our resistivity model. So when we try to interpret our resistivity imaging in terms of something like salinity, we use Archie's law. So Archie's law relates our modeled Earth property, which is bulk resistivity, to salinity, our property of interest. And salinity here is plotted using the practical salinity scale, which is actually a unitless quantity. But it's very similar to parts per thousand, and I've plotted some different water characterizations at the top of this chart. And SW is seawater. And Archie's law depends on porosity variations, and these are measurements that we have offshore New Jersey from those well logs. So I've just filled in different resistivity values between our 2 porosity end members. And I've also denoted 2 different zones with these gray bars. So this first resistive zone denotes sort of one part of our model that we'll look at. And from this, we can really see that any yellow colors, which represent higher resistivities, correspond to fresh or brackish waters. And our conductive zone shows us that when we have more electrically conductive features, those correspond to saline water or even briny water. So this is what our 2D resistivity imaging looks like offshore New Jersey. The color scale is exactly the same, where we have log 10 resistivity and high resistivity is shown in yellow colors, so we know that's low salinity, and conductive features are shown in dark blue, and we know that's high salinity. So here we're looking at 800 meters below the seafloor and about 100 140 kilometers offshore. So this is vertically exaggerated 160 times, just to keep that in mind. So how I interpret this, this image is that we have this sort of duck-shaped aquifer that's very low salinity. The duck's head may or may not be attached to its body. That was something we weren't sure if we were resolving or not. And then the duck is underlain by this deeper conductive feature, which is indicative of briny pore water. So on its own, this image is pretty informative, but it becomes a lot more powerful when we combine other data sets with it. So here we have some seismic imaging offshore New Jersey, and the things that stand out to me are that it seems like the top of the duck's body is vertically constrained by some sort of confining unit, and then the front of the duck's body is laterally constrained by the onset of these clinoforms, which form from prograding deltaic systems. Now we also have all those borehole measurements. So here I've just plotted the locations of those boreholes. And next I am going to plot salinity data on top of those with a white line. So the borehole location itself is going to represent about half the salinity of seawater. So anything to the left of the line, should represent or correspond to yellow regions, and high salinity data to the right of the line should correspond to our blue, more conductive regions. And when we plot all of that data, we do see some pretty good agreement overall, and I'll just highlight a few of the boreholes that agree very well. So this first borehole, we see this sharp decrease in salinity right about where we see the top of the duck's body, and all but one data point show very, very low salinity data throughout the duration of the borehole. So this agrees very well with what we're imaging. We see the similar pattern here where we have a sharp decrease in salinity observed right where we're imaging the top of the duck's body, and then the bottom as well. We see a sharp return to higher salinity data at sort of the bottom of our duck. And then in this borehole, at least in the deeper portion, we're seeing very good agreement with where the borehole does observe brines. So this is up to 55 parts per thousand salinity, and seawater is about 35 parts per thousand. Oops. So brines have been observed here, and that corresponds well with what we're observing in our electromagnetic resistivity imaging. So next I'll move to Martha's Vineyard. Again, we see very similar features. We have the exact same color scale and the same X and Y scales as well. We're seeing an aquifer of low salinity extending to about 90 kilometers offshore, just like we did in New Jersey, which is underlain by brines. And this yellow feature is actually basement rock, which has been identified via seismic imaging. And this is what that seismic imaging looks like. So again, we're seeing really similar patterns where we have a confining unit that seems to mark the vertical extent of our aquifer, and the lateral extent corresponds pretty well with clinoform features. Now, we don't have any offshore drilling for Martha's Vineyard, but there is a well onshore Martha's Vineyard, which observes very low salinities, fresh water in some cases. So this is pretty indicative that this aquifer does continue to the onshore environment. So looking at these two systems as part of a regional aquifer system, I think it's pretty likely that there is a lot of low salinity groundwater throughout this entire continental shelf. So here I'm just going to highlight regions where we've imaged low salinity offshore groundwater. And then given the fact that we do have a lot of onshore aquifers all along this coast, and the similarity between our two profiles, I do think it is likely that this whole hatched region could be underlain by low salinity groundwater. And if this were true, and we just looked between New Jersey and Martha's Vineyard and assumed an average porosity of 45%, which is just sort of our middle value that was observed in these New Jersey boreholes, we would estimate that there's 2,800 cubic kilometers of low salinity groundwater just between our two surveys. And to put that in more real terms, that's like 1 billion Olympic swimming pools or 1.7 times the volume of water in Lake Ontario. So my submarine groundwater takeaways are that we likely have extensive low salinity aquifer systems offshore the Northeast US. These aquifers are connected on shore. The aquifer distribution is structurally controlled, which we saw when we combined our images with seismic imaging. And both the aquifers that we observe are underlain by deeper brines. And just to finally wrap up the talk, I would like to return to my motivating question and of what can subglacial and submarine groundwater systems tell us about the past, present, and future. So with our electromagnetic imaging, we're showing that we have a really nice way to quantify these groundwater systems in both the subglacial and submarine environment. And now that we're starting to get a better idea of what these systems look like, we can start to think about how they might be affecting nutrient exchanges. And in Antarctica, now we can start to incorporate groundwater potentially into ice flow modeling. And in the offshore environment, we've really shown that electromagnetic imaging can be a good way to get a handle on what sort of offshore water resources could potentially be available. And then we can use our electromagnetic imaging again to inform paleohydrologic models, and we can use our paleohydrologic models then to find out what sort of systems were necessary for emplacing this offshore groundwater. And with that, I will end the talk and take any questions. Thank you.
Thank you so much, Chloe. That was a brilliant talk, very clear as well. Some super exciting results there. So everyone, you now have an opportunity to ask questions. So if you can just do that using the chat function, so that should be at the bottom of your screen, presumably. So I'll give you a minute or so now to enter any questions if you have them, or if you would prefer not to use the chat function, then you can unmute and ask the question if you need to. Just while people might be typing in questions, Chloe, I was just wondering, obviously you've done fieldwork not in your kind of standard places, so either from or in Antarctica, what would you say is the most kind of logistically difficult type of fieldwork?
I mean, they're both logistically challenging in different ways. I would say in Antarctica, and I think Carrie might agree, it was perhaps a little more exhausting because at the end of the day, well, at the end of your science day, your work day isn't over because there's always camp chores. We had a team of 4 and we would rotate who would cook dinner and also who would do dishes, and those nights came up very quickly. So I'd say that was probably more exhausting because you really have to, you're not just there to do your science, you're also there to survive, really. And then taking down camp and setting up camp is like a day or 2 worth of work as well.
Yeah, that does sound quite intense. So questions come through from David Teal. Does the change in ice elevation correspond with ice fracture crevasses?
Does the change in ice elevation?
Does the change?
Oh, Yeah. So like, do we have fractures because we have those ice height changes? I think, if I'm understanding.
Yes, yeah, I think that's how I understand.
I don't believe that has been observed before. Most of the crevasses in this area are deeper buried crevasses that have been generated from shear margins further up. I can go to my map actually. Yeah, so cracks or crevasses in this area are most likely generated from these shear margins where you have really fast flowing ice next to slow ice. And then eventually those crevasses do propagate down as the ice is flowing across this region. But as far as I know, there aren't crevasses that have been identified due to these lakes changing in elevation.
No worries. Thanks. So Millicent Crow has a question. In your modeling, have you had any clays or weathered bedrock? Have you?
For the offshore environment? Oh, I can see questions too. Okay. I didn't see the question you just said though.
Yeah, sorry, I got that one sent privately on chat.
Well, I do think that is a good question and sort of brings up one of the limitations of using electromagnetic data is we are just sensitive to electrical resistivity. So clays can also be very conductive, and that's something to keep in mind when you interpret your models. So for our offshore work, we use Archie's law, which I showed here. And this assumes that the bulk of your signal is coming from pore water variations, but it is possible that there are electric signatures that are coming in not just from the water, but from clay as well.
Thanks. The next question is from Kate Selway. She asks, is she right in her understanding that in the Antarctica work, you image the groundwater more than the lake itself? And she asks, was the lake visible at all and were you able to test its thickness, etc.?
So in the forward modeling and the synthetic tests that Carrie and Matt had done prior to our field season, they had predicted that we would see the lake in our magnetotelluric data. But in these models, they didn't include this deeper conductive layer. So right now, Carrie and I think that the conductive layer may be sort of dominating the signal and making it so that it's harder for us to see the lake. But there's still some work to be done on this data set and some tests to run to see whether or not we are sensing the lake at all. And I see that Kate asked about the thickness. I don't think I pointed that out, but the lake itself isn't super deep. When they drilled into it, it was only about 2 meters in depth.
Thank you. The next one is from Doug Oldenburg. What information did you get from the borehole in the Antarctic lake and how did it correspond with your inversion result?
Yeah, that's a great question. So the borehole data actually drove one of our hypotheses for investigating this lake. So the borehole only went down, I think, about 60 centimeters, and we have pore water measurements down to about 35 centimeters, so it's not super deep, but these pore water measurements did get saltier and saltier with depth, so that was an inclination to us that there might be some deeper saline groundwater reservoir, and that idea was initially proposed by Alex Michaud, who did the work on those sediments and pore waters.
Yep. So next we have a question from Regis Neroni. Is MT data acquired over flat ice sheets free of static shift?
Well, we had a problem with one of our stations that we think there was potentially a static shift issue. There's also So I would say no. And there's also special equipment that you do need to use on ice sheets. So ice is very electrically resistive, and that can cause issues with coupling your electrodes to the ice and snow itself. So you have to use not only special electrodes, but also pre-amplifiers in order to sort of get a better signal to noise ratio. And this is something that previous people have done, such as Phil Wanamaker and Kate Selway and Jared Peacock and Graham Hill as well. So luckily, we do have these well-established this well-established equipment for using MT on ice and snow.
Thanks. And the last one is, another one's just come through. So from David Teal, when they were doing VLF measurements in Antarctica, they had a lot of interference from vehicles. Did you have evidence of this in your MT?
The only time we had interference from vehicles were if we were driving our snow machines like right next to the electrodes. And interestingly enough, we actually one day noticed some weird 50 hertz noise in our data. And through a few satellite phone calls, we discovered that there was actually a Kiwi traverse going by, I think still like 100 kilometers away maybe, but we actually did see some of their noise from their instruments, but that's something that we can easily account for in our processing.
Yep, next one is from Remke van Dam. Hi Chloe, great talk. Amazing to do research in two very different settings. Regarding the Antarctica study, it seemed that the bottom of the ice column was fixed at a constant depth in your inversion models. Did you have complementary data for this?
Yeah, this is a great question and something I've been thinking about for the last few weeks. So we know the ice depth from radar data, and we know that it's pretty flat. And so in my initial, we'll just go up to that model. In my initial models, I have been using just ice as 800 meters thick, but there is some variation. It's on the order of a few tens of meters. And so that's something I do want to play around with in my inversions to see if that makes a difference in the results, because it's sort of a little thing, but we do get some interesting effects right at the base of the ice. And I think potentially including a slightly more accurate ice model could improve that, but I'll have to test that out.
From David Annetts, was dimensionality an issue in Antarctica?
Yes, I guess. So something I didn't mention in the talk is that our data that's beyond 10 seconds, so all of this data here looks very 3D. So when I did my inversions, I only inverted data that looked 2D for my 2D models, but we are planning on getting some 3D models running as well, and that will enable us to image the deeper structures.
Great, thanks very much, Chloe. I can't see any more questions coming through, and it's getting late probably where you are in the world. I'll just double check if there's any. Yeah, that's all I can see, except for lots of thanks and well done, and that it was a great talk, which I agree. It was, yeah, really excellent. So yeah, thank you very much, Chloe. And as I mentioned, this will be available on our YouTube channel. So thanks.
Great. Thank you, Kate and ASCG for having me. This was really fun.
Thanks.